So what is it when we say hydrate? A hydrate is a salt. And what is a salt? A salt is an ionic compound. So if you remember the structure of an ionic compound, it looks like this. What is this structure? That's a crystal lattice. And is it solid, liquid, or gas? Are you kidding me? If you had some table salt, is it solid, liquid, or gas? This is a solid. Like when you look at it, does it not look solid? Are the pieces all moving past one another? No, it's a solid. Okay, so that's a solid. And the only thing that's different about a hydrate is, let's pretend that these are little water molecules. Okay, they have an we'll make this part the oxygen, and these two little bits can be the hydrogens. Okay, so this is a water molecule. And do you see how there's holes inside the crystal lattice? Water molecules are so small that they can slot right in there. Okay, so within the crystal, there are actually water molecules embedded inside. Okay, now let's remind ourselves what kind of bond is between this ion and that ion. That is an ionic bond. Okay, between ions, that's an ionic bond. Are ionic bonds strong or are they weak? They are strong. Okay, ionic bonds are strong. These water molecules, they're not held by ionic bonds. They're not held by covalent bonds. They're held inside the crystal by much weaker forces. Those forces are called intermolecular forces. So let's just write down that term, intermolecular forces. The prefix inter, you guys know what the prefix inter means? It means between. So if you go on an international flight, you are traveling in between nations. Yes? If you have an intercontinental sort of thing, you are traveling between continents. Okay, I don't know. International is a good one. I like that one. Now, intermolecular means between molecules. And so if I have one water molecule, I've got an oxygen, and I've got a hydrogen, I've got a hydrogen. And let's say I've got a little puddle of water, and I've got another oxygen, and a hydrogen, and a hydrogen. Do you see how there's a space between the water molecules? There's a little space, but there are these forces between the water molecules that cause them to stick together. That's why water is a liquid. That's why you get a puddle of water, because the water molecules are sticking to each other. If they weren't stuck together, you would have a gas where they're all separate. Okay? So water molecules can stick to each other via these intermolecular forces. And we're going to call those IMFs, because intermolecular forces is really, really long. And they stick molecules, remember MC for molecule, together. but intermolecular forces are weak. Okay, compared to other things, they're quite weak. This ionic compound, remember, it's held together with ionic bonds. Remember I said ionic bonds are strong. So if I eventually wanted to break these bonds, I would have to heat this thing up so hot that the particles moved so fast that these bonds would break. Now, if this is a very strong bond, I would have to heat the temperature very, very, very high. Can you imagine how much temperature you need to melt some salt? Yes? Very high temperature. Okay, so if you put some salt in a pan on your stove, it would have to like go to a very, very, very high temperature in order to melt. Usually people do it in like a crucible and with like a flame and stuff like that. On the other hand, at what temperature does water go from being a liquid, where the water molecules are stuck together, to being a gas where the water molecules are apart? At what temperature does that happen? Liquid to gas for water. 100 degrees. Yes, that's the temperature at which water boils. So liquid to gas, 100 degrees. So that's a lot lower temperature than salt. If you put salt at 100 degrees, it'll just sit there and be like, I'm still salt. I'm still just here. I'm still a solid. Okay, because the bonds are really strong. But the forces between the molecules are quite weak, so at 100 degrees they will separate. Okay? Now, a few other words we need to know. We have a hydrated salt, which is just another word for a hydrate. That is the same. And remember, the hydrate is the salt that has water molecules embedded in the solid crystal lattice. Okay, so the water molecules are inside the crystal lattice. Now we're going to talk about dehydration. When we talk about dehydration, that means removing water. And this is what we are going to do next week in a lab. Okay. We are going to take our salt, which has water molecules embedded in it. Okay. And we're going to put some flame underneath it so it gets hot. And what happens to particles when they start to get hot? They start to move faster and faster and faster. Now, are they going to be moving fast enough to break these ionic bonds? Probably not, because you have to get it to a very high temperature. However, it will be moving fast enough to break what's holding the water inside? What's holding the water in there? The intermolecular forces, because those are weak. Okay, so it gets hotter, they're going faster and faster, and all of a sudden it's so fast that, okay, those intermolecular forces broke and the particles escaped as gas. So you have gas molecules escaping from inside the crystal, but the crystal stays intact. Yes? So we have the water, which is held in the solid crystal lattice by the weak intermolecular forces. And those intermolecular forces will break when heated. But the ionic bonds that hold the cations and the anions together do not break because those are strong. Okay, so the ionic bonds are strong, the intermolecular forces are weak. And that process where we get rid of the water, and now we have a salt with no water in it, that's called dehydration. And what we're left with after we've removed the water is the anhydrous salt. The anhydrous salt, oh my gosh, this is totally wrong. It should say a salt without the water molecules embedded in the crystal. Put a star on that and say fix it, because that's not even a typo, that's just a huge error. Okay, so this is the anhydrous salt. There's no water inside it. Okay, with the water inside it, it's either called the hydrated salt or just the hydrate. So here's a little picture kind of showing what happens. All right, so we have calcium sulfate. All right, and inside we have those two water molecules. What kind of thing is this in between the positive ion and the negative ion? How would I label that? What is that? What kind of force is that between the positive ion and the negative ion? That is an ionic bond. Is it strong or is it weak? It is strong. Okay, now inside the spaces in that crystal lattice, we have the water being held to the ions by these forces. And what do we call those forces? Those are the intermolecular forces, also known as IMFs. Are those strong or are they weak? They are weak. So now we heat this crystal with the water in it, just like I did when I was up here holding it and jiggling around. Okay, we heat it. Which ones break? Do the ionic bonds break? Nope. Do the intermolecular forces break? So when we heat it, the IMFs, the weak IMFs break. But the strong ionic bonds stay intact. And you remember when I flung those water molecules off to the side? That's what we have over here. We have water, gas, and water, gas. Is good? Okay. Many students think that when a salt has water, it must be a liquid or it must be aqueous. That's not true because there's so little amount of water. It's just that water molecules are really tiny and they can just kind of get stuck inside. Okay, so it's not a liquid. A hydrated salt just has a tiny amount of water stuck in between the bits of the solid. All right, how do we name hydrates? And this is what is going to relate to quiz 11 and quiz 5. So we're going to look at following the normal rules for naming ionic compounds. That's for quiz 5. We're going to use Roman numerals for the metals that need it. Who are the metals that need Roman numerals? They would be in the gray zone. And we will not, no Roman numerals for metals that don't need them. Who are the ones that don't need Roman numerals? Anything that is not in the gray zone. And if anyone has been away and is like, what are you talking about? What is this gray zone you are talking about? Let's go look at it. Okay, on this particular one, it's a red zone because I happen to have nicer colors. But it's everything except for these bits on the right, okay? The 3 columns on the right, this little staircasey bit in the middle, and of course none of the non-metals because Roman numerals are only ever used for metals, never for non-metals, okay? So on your, if you don't have a yellow periodic table, make sure that you get one today, all right? Now, the only thing that's different is because it's got these waters tacked onto the end, we're going to use the word hydrate. And depending on how many waters, we're going to use the prefixes to let you know how many waters. And what are the prefixes? They are identical to the ones that you already learned. Mono, di, tri, tetra. So you don't need to learn anything new or different. Okay. So let's take a look at this formula here, okay? And I like this one because it's got a lot of letters in it. And sometimes that confuses people, so I want to make sure we've done an example like this. So many capital letters in this name, yes? Ionic compounds always start with a metal or a polyatomic cation, which is NH4. Okay, so the metal or the NH4, that is your cation. That's the positive ion. And then there's just going to be an anion, just one anion, not multiple anions, just one type. Okay, you might have more than one of that particular type, but then you'll just have plus n anion. So when you are looking at your formula, you can identify the cation all right, and we know that that's the cation because it's NH4, so it's either going to be NH4 or the metal, and then everything else afterwards is the, actually I should do it above because I have more room there. Everything else is the anion. I don't care how many letters come after that cation, that's all anion. All right? If you look and you see I have 2 capital letters here, I have N and I have H. That means there's more than one atom, which means I need to look that up on my polyatomic ion chart. That's the pink sheet. If you do not have a pink sheet, go get yourself one. They're up on the table here. Have your pink sheet out so you can please look up the name of NH4. And maybe you know it already. I hear a lot of people who know it already. It is indeed ammonium. Okay, so NH4 is ammonium. And then you're going to go look up C2O4 also on the pink sheet. So we're going to go up here and look up. So there is ammonium. You'll notice that There's not very many positive cations. There's ammonium and there's mercury 1. Thank you. Now, when we look for C2O4, sometimes people get confused. They see CrO4 and it looks similar, but it's not C2O4. So keep going, keep looking for CrO4, and you'll eventually end up over here. C2O4 is oxalate. Don't do anything to that name. Polyatomic ions, you just name them and then you don't do anything with that name. So here we go. We have ammonium and then we have oxalate. So if this were quiz number 5, the question would end there and you would be done. You'd be like, yay, I finished that question. But here for quiz 11, we have this dot, which we'll talk about in a moment. And then we have an H2O. There is no number here, no number. Therefore, we have 1 water. If we had 2 waters, there would be a 2 in front of it. If we had 3 waters, there would be a 3 in front of it. But there's no number, so it just means that there is 1. What's the prefix for 1? Mono. And instead of writing 1 mono water, we write mono hydrate. Why don't we say mono water? I don't know. Because, you know, we needed to make you learn a new word because you needed more of those, right? Now, one thing I wanted you to notice here is this dot in the formula. That is a dot. It's not a time sign. Okay, the dot is not a time sign, so don't say times. It just means that the water is held in the crystal by intermolecular forces. Loosely held in the crystal by what forces are holding it in the crystal? Intermolecular forces, IMFs. That's what the dot is for. Do I put a dot in the name? Do you see a dot in the name? Did I put a dot in the name? No dot. Okay, no dot in the name. Only in the formula. Okay, another example, Ca3N2. So we say to ourselves, I have Ca, that is the metal, and its name is calcium. Doesn't matter if you put a capital or not. Calcium. Does calcium need a Roman numeral? No, it is not in the gray zone. It's in column number 2, which is not gray. All right. So no Roman numeral. And we just have N. It's not a polyatomic ion. It's just nitrogen. So what do we do with the ending to that name? We call it nitride. Yes. Okay, so calcium nitride. And if this were quiz number 5, you would be done at this point. When you get to quiz 11, you have to add in the 2 waters. And we don't say 2 waters, we say di and then hydrate. My glasses are steaming up. Okay. All right, I love this example because it's got like so many capital letters in it, it's crazy, right? And sometimes those will be people who will look at it and be like, I don't know what to do with that. Remember, you're looking for either your metal or NH4. Who's the metal here? K. K is the metal. And that means that everything else, doesn't matter that there's like 5 letters there, is the anion. So we have potassium. Is potassium in the gray zone? No. So no Roman numeral. And then we go and look up CH3COO on your, where do you find it? Pink sheet. So let's go look. Grab your pink sheet. CH3COO. So you might find it here, in which case you could name it acetate. You will actually also find it down here, which means you have the alternative of calling it ethanoate. Both of those are acceptable names. Acetate is the common name, ethanoate is the official name. So either way is good, just don't name it both things. So we go back here. Okay, so potassium, acetate. Do I put a dot? No, no dot. And then I write, I want to say 3 waters. Instead of 3 waters, I say trihydrate. One more example, because iron, Fe, is in the gray zone, so it does need a Roman numeral. Now, when we're trying to find the Roman numeral, we write out our ions. We say I have 1 Fe. So I write up 1 Fe. How many PO4s do we have? Just 1. Okay, I've got 1 PO4. Don't be tempted into thinking because there's a 4 there that you have 4 of them. PO4 is a P with 4 O's attached. If you wanted to have 4 PO4s, it would have to be PO4 in brackets with a 4 on the outside, and that's not what we have. So we just have 1 PO4. We look up the charge on PO4, that is on your polyatomic ion table, it is 3 minus. That gives us a total negative charge of 3 minus. Fe, then we need a total charge of 3 plus. There's only one place to put all that charge. It all goes on the iron, so we have iron 3 phosphate. And that would be all you would need for quiz 5, but we are doing some hydrate stuff. So we would now not add a dot, that's just for the formulas, but we have 4, which is tetra, and then hydrate. So technically now, if you followed all of that and you didn't need to practice, you'd be ready to do both quizzes 5 and 11. Maybe you want to practice a little bit though, okay? And before we do that, we're actually going to get you ready also to practice for quizzes 7 and 11. we're going to go from the name of the hydrate to the formula. So let's take a look at this one. Copper 2 sulfate. This is what you might see on quiz number 7, just the copper 2 sulfate without the pentahydrate. When you have a name, you're going to write out the ions. We have copper, Cu, so you write its symbol, and you need to find its charge. Can you find the charge for copper on your periodic table? No, you can't. If we go to our periodic table, you will see that copper is not in one of the columns that has distinct charges, right? We know that column 1 is +1. We know column 2 is +2. This one is +3. We know that aluminum is 3+, gallium 3+, zinc 3+, or zinc is 2+, cadmium 2+, and silver is just plus. Okay, we know those ones, but we don't know copper. So we have to figure out copper, but it's not hard to figure out copper. Oops. Because it tells us that 2 is the charge. So we have copper 2+, sulfate. When you see the 8 ending, that tells you you have a polyatomic ion. So if you see 8 or 8, you know for sure you have a polyatomic ion. So you look on the pink sheet. So look on the pink sheet for sulfate, and you will find it is SO4 with a 2-. We want the compound to have an overall charge of 0. So when we add up that 2+ and our 2-, do we get 0? When we add up the 2+ and the 2-. Yes, we do get 0. So that's all we need. The charges balance out and give us 0. So our formula then will be Cu, we just need 1, SO4, we just need 1. Now we need to add in the pentahydrate. So penta means 5, we write a coefficient of 5, and then hydrate, you write H2O. What goes between the copper sulfate and the hydrates? The dot. Okay, it's in the middle. It's not at the bottom, it's not a period, it's in the middle. Barium is in column 2, so it has 2 valence electrons. So when it becomes an ion, it loses 2 electrons to become positive. 2, so barium is 2+. Hydroxide sounds like an element almost, right? It's got that "ide" ending. You need to bear in mind that this is a polyatomic ion. It's a really common one, so hopefully you'll just see it a lot and get used to it. This is a polyatomic ion. It involves both hydrogen and oxygen. And it is OH negative. Have we balanced our positive and negative charges? No. We have 2 positives, but we only have 1 negative. How can we fix that? We're going to add another OH-. That's going to give us a total of 2 negative to balance out the positive. And when we write our formula, we write BaOH2. Somebody's shaking their head at me. What's wrong with what I've written? I need brackets because right now, this 2 only refers to the hydrogen, right? I have 2 hydrogens, but I also have 2 oxygens. So I need brackets so that I get both 2 hydrogens and 2 oxygens. And now hepta, what does hepta stand for? 7 hydrate, I write H2O, and in between those two I need to write a dot. Okay, so in the name there's no dot, but in the formula there is a dot. And that's it for today's lesson. Okay, so your objective today, first objective, get your name off the board if you possibly can. If you cannot get the name off the board today, please come see me either after school today or Tuesday during flex. Okay. And after that, you're working through quiz 6. Just keep going. I've got people who are finished. I got one guy in block 8 who's finished quiz 13. Like, where's quiz 14? I'm like, yeah. If you've done it, then we can get you off there. Where are you? Oh, thank you. And if you've finished the quiz and you need your name off the board, please feel free to come and erase it yourself if you've already written it. Oh, they're in the basket. Perfect. Wonderful. Thank you. Have you done 5? I don't know. I don't know. I feel like you did 5. I feel like you did 5. Like I feel like it was out of order, but you did 5. And then you went back and did 2. I think that's what you did. Yeah, I'm pretty sure. Yeah. Where's my book? Here, there we go. I'm sorry. I'm like so messy here. I'm one of these people who has stuff
You're a teacher.
everywhere.
There's even more stuff I have to pick up. My room's messier, don't worry.
Oh, I tell you. Okay, so we are block 3 and Max. Yeah, I got quiz 5 from you, so we're good. I just did 3/4. Yeah, and you've just done 3/4, so I'll mark those and get those in. So you're good? Yay! And if you need a periodic table, don't be shy. There's one up here.